Hi, good afternoon. It's my pleasure to introduce today's speaker, Professor Sukanya Chakrabarti. Sukanya is a Pei-Ling Chang Endowed Chair at the Department of Physics and Astronomy at University of Alabama, Huntsville. So she did her PhD from University of Berkeley and held postdoctoral fellowships at Harvard and Berkeley. This is the period probably when we first met. She had come for the ICGC in 2012 and had her first introduction to the GR and astronomy community in India, and she's now, she'd been working hard for the last 10 years and also family, but she's back in India and exploring possibilities of how she could re-engage with the Indian community. So she works on the probe of mass distribution in the galaxy. She has started measurements of, precise measurements of very innovative kinds, and she was describing a few to me in the morning, and I believe there would be reasons for a lot of overlap with various astronomers across the country as well as at RRI. And she has also won quite a few known fellowships, Scialog Fellow, IBM Einstein Fellow, as well as the Vera Rubin Distinguished Visiting Professor at UCSC, University of California, Santa Cruz, and also interestingly will be the upcoming Margaret Burbridge Visiting Professor at University of California, San Diego. Okay, great. And she'll be giving us a talk on the precision frontier of dark matter constraints from direct acceleration measurements. Sukanya.
Thank you so much. It's wonderful to be here. It's been quite a long time since I was in India, so I'm particularly grateful for this opportunity to speak with you all today. So I'm going to talk about techniques. Can you all hear me in the back? Yeah? Okay. So I'm going to talk about techniques that we've been developing over the last several years that now enable us to directly measure the tiny accelerations of stars that live within the gravitational potential of our galaxy. Now these accelerations are at the level of about 10 centimeter per second over a decade baseline. Now that's the speed of a crawling baby, and not a very fast baby at that. But as you'll see, measurement of these tiny baby accelerations gives us the most direct window into the mass distribution of our galaxy, both the visible stars and the elusive dark matter that astronomers have been trying to understand for more than a century now. But let me start with the story of our universe as we understand it currently, where dark matter is a key player in assisting the growth of structure in the universe. So the universe starts out when it's a baby, it's very smooth, like most babies are, but it has tiny fluctuations that are amplified by gravity to produce the galaxies and the galaxy clusters that you see today. The movie that's running is a computer simulation of the growth of structure in the universe, starting from these very smooth initial conditions, the baby universe, and evolves forward to present day to the adult universe. And these are now increasingly more sophisticated simulations that have included the role of supernovae feedback, which dumps metals into the surrounding environment, polluting it, from which further generations of stars are born. And here in this picture, in this cold dark matter paradigm, dark matter provides a basic scaffolding that lends a stability to galaxies and enables structure to grow efficiently. And there are many lines of evidence from gravitational lensing, from the observations of rotation curves of the edges of galaxies where there's very little visible mass, but still see that things are moving much faster than what we expect on the basis of the visible mass that indicate that dark matter exists. But what we really don't know is what is the nature of dark matter. Okay, what is this? What is the type of particle that we can attribute to this thing that we call dark matter? There are several popular candidates out there, and they have very different distributions of mass within galactic scales. And what we're trying to do with our measurement campaigns where we're going after these tiny baby accelerations, we're trying to determine from measurements of accelerations directly what is this dark matter? Is it more like this whole dark matter paradigm, or is it more like this warm dark matter paradigm that looks substantially smoother on subgalactic scales? So that's really our long-term goal. Now, traditionally, what's been done in the astronomy community is we had estimated accelerations by modeling a snapshot in time of the positions and speeds of stars under certain simplifying assumptions, particularly the assumption of equilibrium. But you can do simulations in interacting galaxies, and you can see that the true acceleration, when you have a time-dependent potential, when you have an interacting galaxy potential, is in fact quite different than what you get if you assume equilibrium and do the so-called what is known as kinematic analysis. And we now have many lines of observational evidence that show that our galaxy has had a highly dynamic history, that it is out of equilibrium, and I'll remind you of a few of these examples. This is from analysis of Sloan Digital Sky Survey data that showed that there is an asymmetry in the star counts in the north of the galactic disk versus the south. Okay, that is, there are more stars in the south of the galactic disk than there are in the north. So it's kind of wobbling, okay? As if our galaxy was perturbed by a passing dwarf galaxy. And this picture of the galaxy being in disequilibrium has become even sharper since the release of Gaia data. This is the so-called Gaia-Enceladus merger that is believed to have shaped the thick disk of our galaxy.
Sorry, I'm just the previous picture that you just showed.
Yeah.
This one, is that supposed to be the dark matter?
This is showing, sort of the locations of the motions of the stars that are attributed to this dwarf galaxy merger that's been termed the Gaia-Enceladus merger, almost a major merger that is believed to have shaped the So not only in the stars, but also in the gas, the cold component of our galaxy, we see evidence of disequilibrium. So this is the projected gas surface density map of the neutral hydrogen in our galaxy. And in the outer parts of our galaxy beyond the solar circle, you can see that it's not uniform. There are large splotches, there are spiral structures, there are large perturbations that are difficult to explain in a purely isolated context. And now, before I worked on precision measurements, I worked on simulations of interacting galaxies for about a decade, which has informed my perspective of how I think about things, and I'll just review some of the work that we did briefly in that context. This is a computer simulation of the Milky Way interacting with the Amphia 2 dwarf galaxy. This is the stars, and you can see as the Amphia 2 dwarf galaxy got too close to our galaxy, this is an act of cannibalism, galactic cannibalism. You see this tidal stream stripped stars from this tiny dwarf galaxy. And this is the response in the gas. And with my students, we've looked at the formation of the Magellanic Stream arising, which is this long gaseous feature that stretches across the sky. And here we've included both ground pressure stripping and tidal stripping effects. Now, the one constant across one constant across all of these simulations. The galaxy is changing. And we are now entering an era where we can directly measure that change. Okay, so we can move beyond the traditional based descriptors to real acceleration measurements that are derived from time series, extreme precision observations. So essentially, very similar to if I were to drop this thing, you could take a bunch of pictures of it, and you could figure out the gravitational potential of the Earth. That's essentially what we're trying to do. Except in our case, it's a lot harder, because galaxies are big, time scales are long, accelerations are really tiny. That's why we have to do it at extreme precision, and we have to wait for substantially long periods of time before we can make these measurements. Yeah.
So what is shown here in the left bottom graph?
What's shown here is there are these two dwarf galaxies that orbit our galaxy. They're known as the large and small Magellanic Clouds. And what you see is the interaction of the gas as it's moving, the gas from these two dwarf galaxies, as well as the tidal interaction between this sort of pair of dwarf galaxies as it's moving through the dark matter halo of the Milky Way. So it's a computer simulation, including the gravitational potential of the Milky Way, along with these two dwarf galaxies that are in orbit around our larger spiral galaxy. So there's several techniques that we have developed over the last now 4 years that I'll talk to you about. And I've been fortunate to work with a fantastic group of collaborators, students, and postdocs, some of which are shown here. And this is a really very multidisciplinary group, including folks from the exoplanet community, the pulsar timing community, people who are working on close binaries, and also traditional galactic dynamics as well. Now, let me set the stage by first talking about the measurement of big accelerations that the astronomy community has been very successful at for many decades now. And the most well-known example of this is the measurement of accelerations of stars near the galactic center, from which Genzel and Guez were able to derive a quantitative measure of the supermassive black hole in the center of our galaxy. And the movie that you see here shows the orbits of these stars from about 2 decades. Okay? And these orbits are derived from the measured accelerations. When you do that, when you constrain orbits from their measured accelerations, you, in a sense, reduce the problem to that of planets in the solar system, which is something we understand quite well. Now, the other area where you've seen significant advances of measuring big accelerations is in characterizing black holes around luminous companions. Now, I want you to notice the scale here on the y-axis. This is showing the radial velocity, that is the line of sight velocity as a function of time. And note that the changes in the radial velocity here are of the order of tens of kilometers per second. Tens of kilometers per second. We're going to contrast that in a minute with the accelerations that we're having. And we've also worked in this field as well of these big accelerations. This is our work on the discovery of the first stellar mass black hole upon the release of Data Release 3. This is this 10 solar mass black hole on a long period orbit that we characterized from follow-up spectroscopy as well as from the astrometry. And again, notice the y-axis here. The changes in the line of sight velocity and the radial velocity are more than tens of kilometers per second. So we're going to move now into the realm of what I like to call real-time galactic dynamics. If you want to measure the galactic acceleration using very precise radial velocity observations, you need a precision, an RV precision of about 10 centimeters per second. Okay, the galactic acceleration is about 10 centimeters over a decade baseline. Let's contrast this with the galactic center accelerations that we talked about. The galactic center accelerations in units of centimeter per second squared are about 0.3 in units of centimeter per second squared. In those same units, the galactic accelerations that we're trying to measure are 3 × 10⁻⁸ centimeter per second squared. So much, much smaller. But as you'll see, we have already measured it with one technique, and in a matter of a few months, we should be able to do it with another technique, and a few years down the road, we have another technique. So using compiled pulsar timing observations, we were able to measure the galactic acceleration for the first time several years ago, from which we were able to derive fundamental parameters that describe our galaxy, like the total midplane density, this is known as the Ord limit, as well as the local dark matter density. So I'll talk to you about that. And another technique, we're working on this quite extensively now, uses very high precision observations of eclipsing binary stars. So two stars are going around each other, and when one star is passing in front, you can have a very deep eclipse. If you can measure the midpoint of that eclipse very, very precisely, at the level of about 10th of a second, you can look at the shift of that eclipse midpoint time over about a decade baseline, which gives you yet another measurement of the galactic acceleration. Now, all of these techniques may seem quite different, but they do have one thing in common, which is their effective precision. And we're talking about accelerations now, so we can express that as a shift in the frequency. So this is almost comparable to the vibrato of an opera singer. So it's an analogy. So you can hear it, and we're now approaching the regime where we can directly measure it for astronomical objects. So let me give you some background here on our acceleration measurements. So let's first look at what the profiles would look like if the galaxy was unchanging. Okay? The galaxy had a time-independent potential if it was static. So what is shown here on the y-axis is the change in the line of sight velocity over a decade as a function of height above and below the midplane for some commonly used galactic potentials. These are time static. And what I want you to notice is that the y-axis here, it's at the level of several centimeter per second, so very small changes. And notice also that it's quite symmetric on either side of the midplane. And let's now contrast this with acceleration profiles of interacting galaxy simulations, like the one that you saw here, the Milky Way interacting with this Anthea 2 dwarf galaxy. Now the same thing is shown here on the y-axis. The blue line, the blue dashed line, shows the equilibrium initial condition, and the green line shows the post-interaction profile. So the top is for the interaction of the Milky Way and this Anthea 2 dwarf galaxy. The bottom is for the interaction of the Milky Way and another dwarf galaxy called the Sagittarius 4. But you'll notice in both cases that the post-interaction profile, the green line, is highly asymmetric in both cases. And that's a signature of the interaction, and that's how they're distinct from these static potentials. And if you do assume equilibrium, as is done in kinematic analysis, you can see that you would, in fact, have a significant systematic error in estimating these accelerations that arises from ignoring these types of interactions.
What do you mean by equilibrium? What do you mean by equilibrium?
What I mean by equilibrium is that there are not, that the galaxy is not changing over time, as would arise from, say, dwarf galaxies perturbing the Milky Way. So the Milky Way is known to be surrounded by many dwarf galaxies, some of which approach, like here, some of which approach the galactic disk and perturb it, right? And that leads to the galactic potential of our galaxy, changing as a function of time. So if you do computer simulations like this, you can look at the potential of the galaxy and you see that it is evolving over time. Yeah.
Yeah, so how often are these disturbances and how frequent are they and how much of a, I mean, this is one example.
Right.
And so that's all for our Milky Way?
These are both for our Milky
Our
Way.
Milky Way.
Yes. So, it depends. We don't have an exhaustive catalog, but certainly for relatively massive dwarf galaxies like the Sagittarius dwarf, I think we have a fairly good idea of that. And those interactions are at the level of several hundred million years or more. But as you go to smaller and smaller mass scales, it's harder, right, especially if you're going to smaller mass scales and going to larger distances, right? Assessing those tidal effects becomes more problematic.
I mean, there must be a regime in which the equilibrium picture looks like reading the picture. But
It's a question. It
time
comes down
scales?
to a question of precision, right?
Oh, okay.
It comes down to a question of precision. So, at the level of the factor few, right? If you want to infer galactic parameters, and you're satisfied with getting them in plane density to a factor of few, you don't need to do equilibrium because it's a lot of work. If you're satisfied with factors of a few accuracy in equilibrium, it's a good assumption. But if you want to do better than that and push the envelope on precision, then I'm arguing that it's important to move beyond kinematics and carry out direct estimation. So, what we're doing essentially is we're adapting techniques from areas in astronomy that have seen significant advances in precision measurements. And certainly one of those areas is in the hunt for exoplanets. And so this is, you have this planet going around the star. The star, of course, tugs on the planet, but the planet also tugs on the star, leading to these small shifts in the spectral lines that we can now measure to increasing precision, as shown on this plot here. This is showing the radial velocity precision as a function of the commissioning year of the instruments. Okay. And, back when I was in graduate school, the first exoplanets, Jupiter mass exoplanets were discovered. That was a big deal, huge deal at the time, right? Several meter per second radial velocity precision. The instrument that we're using today is called Espresso on the Very Large Telescope in Chile, which has demonstrated on quiet stars about 10 centimeter per second radial velocity precision. Okay, so huge, huge improvements. The instruments that will be available on the extremely large telescopes, the 30-meter telescopes, in the next decade will have comparable precision, but of course will be on much larger telescopes. Okay, so they'll be able to make direct acceleration measurements across the galaxy and beyond. Now, one of the big things that we have to worry about in making these measurements are contaminants to the galactic signal. Because the signal that we're after is really tiny, right? So basically anything can be a contaminant. For the extreme precision radial velocity observations, that's the first technique I'll talk to you about today. There are two key contaminants that we have to worry about. They're external to the star. Okay, that is, they're stellar binaries that in principle we have to worry about. There are also planets going around their host stars. And the biggest contaminant, both for us as well as for the exoplanet community, is the star itself. Okay, the star itself is a source of noise for measurements that are where we were attempting measurements at better than the meter per second level. Okay. The stars have internal activity that can confound the signal that you're trying to go after. This is stellar jitter. And this internal activity becomes higher and higher. So stars become noisier and noisier as they get more massive. So we've chosen subgiants as a compromise between the brighter stars that are very noisy but can trace the galactic potential for that, and the fainter stars, dwarf stars that live at the jitter minimum.
Sorry for the distance. The voice is not clear on the YouTube channel.
Oh, okay.
It's
So,
a place of the mic.
okay. I can just stand here if you like. Is that good?
Okay.
Or, okay.
Still it will be just
I see. Okay. Let me stand here if this is yeah, I'll just stand here. So we've looked at both external and internal contaminants in this context. Here, what I've done here is written a population synthesis code where I've incorporated the effects of stellar binaries, planets around their host stars, and of course, single stars that faithfully trace the galactic potential. And this histogram shows the changes in the radial velocity that are induced by these different types of objects. So you can see that binaries lead to large changes, produce large changes in the radial velocity, and so you can easily remove them from the survey. In fact, we've done so already. There is some overlap, as shown in this inset here, between planets going around their host stars. So there can be some contamination from planets, particularly low mass, long period planets. But we think that the overall contribution to the galactic signal should be quite small. So, we are trying to measure the speed of this slowly crawling baby, but we have to contend with fast bunnies and things like that in our survey. But this is really the key challenge for us is this stellar jitter, this internal contaminant that arises from activity internal to the star, arising from magnetic activity, granulation, oscillations on various timescales. So the way we're going about this is, we want to find the quietest possible stars, right? That it will ultimately enable us to make this very small measurement at the 10 centimeter per second level. Our goal is to find the quietest possible stars. We've already removed stellar binaries from our sample. You can see an example here. You see the two peaks in the cross-correlation function that indicate that this is a stellar binary, so these kind of things are removed easily from our survey. And on the right here, you see an example of a star with some excess stellar activity. Okay, the ideal case is shown in the black line, but the somewhat more noisy case is shown in the red line. So there's some excess flux here in the calcium K-line core that indicates that it's going to be a little too noisy for our purposes. And this is how, in our initial cuts, we remove some of these lightly noisy sources. But this is still a relatively low resolution characterization of the stellar jitter. This is what's used typically at the several meter per second level. The best way of doing it is by looking at the scatter and the radial velocity as a function of epoch. And that's what we are doing now to characterize these stars, the quietness of these stars at the meter per second level. So basically, you can figure out that these stars are quiet by basically looking at their spectra. But of course, sometimes there can be some debate on this type of thing. Okay. Now, in the other strategy that we have in the long-term sense is shown here. So this is showing the error in the radial velocity slope. The slope of the RV curve is the acceleration, right? And the error in the RV slope, therefore, is how precisely do you measure that acceleration? Okay, so this is an analysis of radial velocity data from the decade-long LCS high-res survey. This is relatively low resolution compared to what we're doing, but this has already been done, so we can analyze the data and look at trends to get some potential insights for what we're doing. And what you see here is that this is showing the area in the RV slope as a function of number of independent measurements. Okay, and this dashed line here is going as 1 over root n. Okay, so this precision is improving roughly as 1 over root n. So the optimistic thought is that if we can select the quietest stars that are quiet at the level of, let's say, 50 centimeter per second, with 25 independent measurements over 10 years, we can hopefully get to this 10 centimeter per second holy grail. So I'm going to move on now to talk about pulsar timing. So pulsars are fantastic galactic clocks. Their temporal stability even rivals atomic clocks. This is an example of a slow pulsar. You see the pulse profile in the bottom. But the best timed pulsars are these so-called millisecond pulsars that spin hundreds of times per second. So that's a millisecond pulsar. And we have been able to use them effectively as galactic accelerometers, very much like the accelerometers that you have on all your iPhones, by looking at the change in the orbital period for pairs of millisecond pulsars. So in this initial work that we did back in 2021, this is a figure from our press release at the time. We selected a total of 14 binary pulsars. That set has grown since then. I'll talk to you about recent improvements, but this is how we began with a grand total of 14 binary pulsars back in 2021 that are shown here. And also shown here is a graphical representation of our galaxy, this warped ripple disk of our galaxy with a Sagittarius tidal debris superimposed to emphasize this idea of this equilibrium in our galaxy. Now I want to just go through the basic setup of how we're doing this with you. So what we get from Nanograv and other pulsar timing facilities, and I was talking earlier with some of you here who are working on pulsar timing, is the time rate of change, the observed time rate of change of the binary period. That's the quantity here on the left-hand side, the observed time rate of change of the binary period. Okay? That's the observation that we're getting from pulsar timing facilities. On the right-hand side are the physical mechanisms that lead to that change. The first term is due to the fact that these stars live in the galactic potential of our galaxy, therefore they must accelerate. The second term here is the so-called Shklovsky term. Okay, that's the apparent orbital change due to the pulsar's transverse motion. You can calculate that if you have the proper motion mu and the distance d. And this third term is this general relativistic term that arises because these are compact objects on tight orbit, so there's gravitational radiation emission. You can calculate that third term, the GR term, if you have their masses and the eccentricities, which we do from pulsar timing. So you can see that you know everything here except for the galactic term. So that means that you can isolate and solve for the galactic acceleration rigorously. Now, in this initial work, we excluded sources in globular clusters because in those cases, the globular cluster potential dominates, and we only use sources with proper motions and parallax measurements. And I'll go through a simple, very simple, this is just meant to be illustrative. It's not meant to be comprehensive, just to show you the basic idea of how we do this. And this was our initial distribution of the 14 binary pulsars. As you can see, they're relatively close to the sun. The sun is shown here as the yellow star. They're within a couple of kiloparsec of the sun. So I'll go through just a simple illustrative case of how we do this. So let's write the galactic potential in this way, in galactocentric radius and vertical height, and we're going to say that it's separable in R and Z. And we'll write the radial component in this way, where VLSR is a local standard of rest velocity, and beta is the slope of the rotation curve. And continuing to be simple, we'll write the vertical component of the potential in this way, where alpha 1 is the square of the frequency of low amplitude vertical oscillations. Now we're measuring acceleration, so we can very straightforwardly use the Poisson equation. And for the case of beta equal to 0, we have a very simple relation between this alpha 1 parameter, and on the right-hand side is the total midplane density that is in galactic dynamics, that's known as the Oort limit, that until our work had been estimated using kinematics alone. But this is the first measurement of the Oort limit, that is the total midplane density using direct acceleration measurements. So alpha 1 is essentially proportional to this midplane density. These are our posterior distributions from our MCMC calculations, and you can see that the midplane density is quite well constrained. But however, and that's our value there, it's constrained to about 3 sigma. In this initial work, we could not constrain the slope of the rotation curve because the pulsars had an extent of about a kiloparsec in R and Z, so that you get the more significant constraint in the smaller dimension, that is the vertical dimension. And you can subtract out the baryon density, that is the visible stars in the gas, and from this you can determine the local dark matter density, and our value is superimposed here on kinematic estimates that have go back now to more than a century, and we were somewhat on the low side. Now, this year, this is work that was led by my postdoc, Tom Donlin, at UAH. We went back and looked at this again. Pulsar timing measurements and all acceleration measurements, the precision improves with time. And so now, in this year, the sample has grown to 26 binary pulsars. In fact, that's what's published. The full set is actually 28. And so you can see that, as before, we have a constraint on the Oort limit. The Oort limit continues to be tightly constrained. But additionally, you'll notice now beta, the slope of the rotation curve, is also tightly constrained because we now have a much larger radial extent for this expanded pulsar timing sample. So that means that we can characterize the rotational properties of the galaxy, that is the Oort constants, for the first time from direct acceleration measurements. And the key, in addition to improved parameters that describe the smooth properties of our galaxy, the key improvement here is that we can now move beyond smooth descriptors of the galactic potential. Okay, so on the right-hand side is shown an acceleration map of a static galactic potential. And on the left here is the observed acceleration map from the observed pulsar timing sample. And you can see that they're very different. Okay, that is, the observed acceleration map is highly asymmetric. And you can see that clearly if you take cuts above and below the disk. Okay, so if you take, these are cuts below the disk at -1 kiloparsec, at the disk, at the galactic midplane, and above the disk at +1 kiloparsec, and you see that the structure is highly asymmetric below and above the disk, okay, indicating that the observed galaxy in acceleration measurements is not smooth. It's quite asymmetric. And you see the same type of asymmetry when you look as a function of azimuth. Now here, we've compared the measured line of sight accelerations. This is in the gray shaded region, including the uncertainties. Okay, this is shown here above and below the disk, to the Sagittarius dwarf galaxy simulation that we talked about earlier, right? That's also very asymmetric, as well as another galactic potential and harmonic model. And so you can see that this Sagittarius dwarf galaxy simulation that perturbs the galaxy is in fact has some consistency with our direct acceleration measurements for this larger pulsar timing sample, which is quite interesting. Yeah, yes, please.
The potential that you wrote down looked like it was a separable potential, it was isotropic in the radial plane and so on. So
No, no, no. Yeah, no, I did that largely because I just wanted to give you an idea of how we were doing it. That's why I said, it's just meant to be illustrative. And so I just wanted to give you an idea of how we would get things like the Oort limit, right? How we get things like the slope of the rotation curve. So for those, it's okay if you assume a fairly simple parametrized form of the galactic potential, but as you're moving beyond that, right, as you're moving beyond that, at that time we only had 14 binary pulsars, so we were limited in what we could do in terms of describing the data in 2021. But as we move to larger samples, right, and we are able to capture the asymmetry in the that is inherent in the acceleration measurements, we also have to move to much more complex potentials as well. Does that make sense? Yeah.
Was this, you have this parameter beta, which was negative in one bit and became positive in the
No. In the original case in 2021, we simply could not constrain it, right? When your PDF from your MCMC calculations doesn't have, isn't strongly peaked, that just means that we have no constraint on the slope of the rotation curve, and that's expected in that context, right? Because the pulsars, in 2021, back then, the pulsars had a radial range of about a kiloparsec in radius and vertical height. So we could get a significant constraint in the vertical dimension, the smaller dimension, but not in the radial larger dimension. And that changed significantly as we went to this larger binary pulsar sample. Now, so far we have made the restriction of using binary pulsars only. And the reason I'll remind you is, what we have here is the observed quantity, is the observed time rate of change of the orbital period for pairs of pulsars. And we know everything on the right-hand side except for this PB dot term that arises from the galaxy. So we can do it rigorously. But not all pulsars are in binary systems. There are lots of pulsars that are solitary. So this restriction limits our sample. And so it'd be great if we could use the time rate of change of spin periods to measure accelerations. And you can think about writing down a similar equation if you're using the time rate of change of the spin period. Okay, so you will still have this galactic term, you'll still have the Shklovsky term. But now, okay, you have this magnetic braking term, this third term here, which is not understood at all, and that's why we don't even know the magnetic field is necessarily dipole in nature. And that's why we had initially restricted ourselves to binary pulsars, right? Because we don't know a priori how to get this magnetic braking term. But what we realized is that for the case where we do have measurements of the galactic acceleration for the set of binary pulsars, right? For the set of binary pulsars where we have measured the galactic acceleration, we can say very simply here, what this equation says is that the galactic acceleration is equal to the galactic acceleration. I can express that either as the time rate of change of the binary period, or I can express that as the time rate of change of the spin period. And for the set of 26 pulsars for which I do have measurements of the galactic acceleration, I can carry out a simple empirical calibration of the magnetic braking term that depends only on observed quantities. And if you restrict yourself to small surface magnetic fields and large characteristic ages, this allows us comparable accuracy as what we had from the binary pulsars, and it expands our sample to 54 sources and nearly doubles the previous sample. And so now we can look at really a wealth of disequilibrium phenomena in the galaxy, including this north-south asymmetry, that is, there are more stars in the south below the galactic disk than there are in the north. We can look at the effect of the Large Magellanic Cloud as it's moving towards our galaxy. It leads to an offset between the disk and the halo of our galaxy as it's perturbing our galaxy, this dwarf galaxy. It's perturbing our galaxy as it's moving toward it. And we can include all of these disequilibrium mechanisms, okay, in a model as we're comparing to the observed acceleration, okay? But there's still some small discrepancy that we have yet not included, which is quite interesting. So this may arise from some yet new mechanism that is not known, or there may be systematics in the pulsar observations that we don't yet understand. And this large sample, this largest sample to date, now also gives us the first constraint, direct acceleration constraint on the local dark matter density that's shown here in the red star there. And you can see here kinematics estimates as well. I'll just point out that the kinematic estimates do not include the systematic error that arises from ignoring disequilibrium. Okay, so the error bars are not reflective of that. The other, I think, very important thing here is that, you really get a lot of bang for your buck with direct acceleration measurements compared to kinematics. So this, and I want you to look particularly at this bottom plot here, which is showing the uncertainty in the local dark matter density normalized to the number of sources, okay, for pulsar accelerations today compared to kinematics. Okay, right now, today, a single new acceleration measurement gives you about 5 orders of magnitude more precision than a kinematics measurement. Okay, so that's a lot of bang for your buck for acceleration measurements compared to kinematics. So basically, what we're trying to do is we're trying to develop astrophysical time standards, of which pulsar timing is one. But there are, like with any technique, there are inherent systematics, right? So, you can't, if you want to assess systematics in pulsar timing, you cannot do that with pulsar timing. That can only be done with another precision technique. And so let me talk to you about eclipse timing, which is something that we've been working on quite extensively. So if you have 2 stars going around each other as one star calls the other, the brightness varies as a function of time, right? You can have, in some cases, quite a deep eclipse. If you can pinpoint the midpoint of this eclipse very precisely, if you have a very high signal-to-noise light curve, if you can pinpoint the midpoint of this eclipse to 1/10 of a second or better, that gives you yet another measure of the galactic acceleration, okay? The shift in the eclipse midpoint time that arises from the galaxy can be expressed in this way, and this is an equation that you can recognize, that you are in fact familiar with. If you'll note that this term here, this PB dot over PB, that is an acceleration modulo the speed of light, and so this is an acceleration times the time baseline squared. This capital T is the time baseline. Now, this is, we're in a very fortunate position today because it's been about a decade since the Kepler mission got very high photometric precision observations of eclipsing binary stars. And so today, with space-based observations, with very high photometric precision observations, we can measure this shift, in principle, for hundreds of eclipsing binary stars. And as before, we have to think about contaminants to the galactic signal that can arise from tidal decay, from rotationally and tidally induced quadrupole moments from planets, et cetera. So all of these different dynamical mechanisms, okay, these ith dynamical mechanism can lead to a shift in the eclipse midpoint time, delta TC. And these are shown here color-coded on this plot as a function of the binary period. The solid green line is the galactic signal. What we really want to do is to populate this kind of plot with real sources. And we can do that because work by Eric Eagle and others in his group led to a calculation of the stellar and binary parameters for about 700 eclipsing binary stars. Okay, so that means I can calculate all of these different terms on the right-hand side, and they're shown color-coded here on this plot. So the green line is the galactic signal. Okay, so you'll see that there are hundreds of sources that lie below the green line, such that all dynamical effects are much smaller than the galactic signal. And so if we go after these type of sources, we should be able to measure the galactic signal from the shift in the eclipse midpoint time. And we've also looked at the effects of circumbinary planets in this kind of population synthesis model and concluded that it should be not significant. So this is showing our estimates for, in the Kepler field, the timing precision. We expect that many of them should have sub-second timing precision. This is our sort of prototypical eclipsing binary that we're going after. We want very deep eclipses. Stars with very deep eclipses are the ones that are easiest to time. These have the best timing precision. This is a simulated HST light curve. And we do need very high photometric precision, very high signal-to-noise light curves to enable us to carry out these type of measurements. And we applied for HST time, and after only 3 attempts, we were finally awarded HST time. And so these observations should occur sometime in the next few months. Now, in the meantime, we're also trying to do this from the ground. Another class of objects that are fantastic timing precision are eclipsing double white dwarf systems. Okay, this is our own data using the high-speed photometer HyperCam on the 10-meter telescope in Spain. At the moment, what we have is an upper limit on the Oort limit, but we think with a few more measurements, we will get, this is an expectation here, scaling the error with the number of measurements, but we think that in a few more months, we ought to have the first measurement of the Oort limit, the total midplane density with eclipse timing of this double white dwarf system. So that's in the very, very near future. So going back now to this idea here, right, these different popular dark matter models have very different distribution of substructure on galactic scales. And this is really, what we're trying to probe with our acceleration measurements, right? We want to look at these differences in the mass distribution, which effectively would correspond to sort of what are known as jerks in the acceleration field, that is the second derivative. We are trying to do this also with our extreme precision radial velocity sample that we're observing with the high precision espresso spectrograph. So shown here is the binary pulsar sample in the red and our extreme precision radial velocity sample in the blue. And our EPRV sample is designed to be very different from the pulsar sample. So it much more densely samples this vertical region here with the hope of detecting the differences in substructure between various different popular dark matter models. So this is showing all our observing campaigns here in galactocentric radius and vertical height, and they're color-coded, our extreme precision radial velocity sample in espresso, in the green, the binary pulsars in the red, the eclipsing binaries in the Kepler field in magenta, and our double white dwarfs in the white. And so, one of the things that's really struck me is that I think there's really a synergy between precision tests of dark matter that we're engaged in, as well as precision tests of GR, for example, that are done in the pulsar timing community, where currently the galactic potential is the largest source of uncertainty. So what it's done traditionally, and what has been done to date in the pulsar timing community, is you assume a kinematic potential. Okay, that leads to systematic error in tests of GR. which we ought to be able to rectify in the next few months with these eclipse timing measurements of the galactic potential, direct acceleration measurements of the galactic potential. So this is an animation that folks at the Space and Rocket Center did for me, showing first our initial set of binary pulsars overlaid in our galaxy, the expanded binary pulsar sample. This is the set of single pulsars, the 54 pulsars, our eclipsing binary sample, the double white dwarfs, and finally our extreme precision radial velocity sample. So this is a network of accelerometers across the galaxy that's shown here. So, I like to show this sometimes, and I update it as we're going along to see if we're staying on track. So, in 2021, we started with this relatively small sample of 14 binary pulsars from which we were able to measure the galactic acceleration for the first time. We also began our extreme precision radial velocity survey, selecting the quietest stars, and then entering into our monitoring phase. Earlier this year, Tom Donlin was able to expand our sample of binary pulsars to 26 binary pulsars. And we're now in the process of carrying out eclipse timing measurements using eclipsing binary stars, as well as eclipsing double white dwarfs, using HST as well as hypercam on the 10-meter Spanish telescopes. The pulsar timing sample has now grown to 54 sources. We expect to publish upper limits for our extreme precision radial velocity survey in a couple of years, and we expect to publish the full measurements shortly after the decade. So I'll go ahead and summarize. We've been able to measure accelerations directly using pulsar timing, and we expect to do this with other techniques very soon. We find that the midplane density and local dark matter density are close to, but slightly lower than modern estimates. With the expanded pulsar timing sample, we can constrain not just the midplane density, but also the slope of the rotation curve. And the larger pulsar timing sample now allows us to characterize the disequilibrium in our galaxy to a significant level of detail, as well as enable constraints on the local dark matter density for the first time. And my hope is that, this first galactic scale EPRV sample, EPRV survey that we're doing will serve as a pathfinder for what can be done in the future in the next decade by the extremely large telescopes that should enable direct acceleration measurements across the galaxy and beyond. And I'm hopeful that the combination of these various techniques will shed some light on the nature of dark matter. I'll end there. Thank you so much for your attention.
So, going back to your, this different dark matter models that you showed and discriminating between them. So, there are other ways to distinguish these different dark matter models. Now, how does this approach compete in just simple terms of, some figure of merit or something? It's like comparable or?
Yeah, so that's where we're headed. We're not quite there. The expectation is, for example, if you were to try to detect dark matter subhalos, for example, right? We expect that we ought to be able to do that down to sort of interesting mass scales at the level of, say, 10 to the 6 solar masses, or below, where there are very few stars and where acceleration measurements become a really interesting probe, when you have about 100 sources. And we're just approaching that, so we're not quite there. But, you know, as I said, I would say that we will be competitive very, very soon, right? Because you know, this figure here, what we're showing here is the uncertainty in, as a figure of merit, the local dark matter density normalized to the number of sources. And you can see, if you compare the orange symbols that show the pulsar accelerations to the yellow, to the blue that show the kinematics, there's about 5 orders of magnitude difference here. So one acceleration measurement is much, much more precise than a kinematics measurement, right? So we're not quite there in terms of discriminating dark matter models, but we will be in the very near future. And we are not subject to the assumptions that kinematics analysis is subject to, right? We don't assume equilibrium, right? We're measuring the acceleration today. So we're very nearly there, but we're not quite there.
And what about very local disturbances like, I don't know, maybe an unknown black hole in that region which is disturbing the trajectories? Is that
Yeah, absolutely. We would be sensitive to those kind of disturbances as well. You know, it's really a question of how large the disturbance is and how many sources you need in an effective region to probe, right? To probe that type of disturbance. But in principle, we're sensitive to any type, right? Any type of disturbance which will impart a feature on the acceleration profile.
Maybe very naive question. So, so we are seeing from the Earth. So we are already accelerating. So when you are observing the accelerations, are you correcting for these?
Yes, yes. So that's a very good question. So what we are actually looking at here is the relative acceleration, okay? Right, it's the relative acceleration that is between the sun, the Earth, and the system that we're looking at. And so what you have to do is subtract out the acceleration of the solar system barycenter. So that has been done in everything that I'm showing here.
So what about 10 centimeter per second? You talk about that thing.
Mm-hmm.
So what about that 10 centimeter per second if galaxy is not symmetry, the acceleration is not symmetry or some homogeneous?
Right. So that's sort of rough measure just to give you an idea of what we're aiming for. In some locations of the galaxy, right, so for example, here, you know, in some parts of the galaxy, like if you're looking below the galactic disk for this interaction with the Sagittarius dwarf, right, it can be quite different, right? Below the disk versus above the disk. In fact, it can be quite different, but the 10 centimeter per second is just intended as a rough characterization of the RV precision that you need to measure these changes using extreme precision radial velocity observations. I'm not saying that it's always 10 centimeter per second everywhere you look in the galaxy, and this figure is intended to demonstrate that in fact it is quite asymmetric, right? You know, you see that below the disk and above the disk, it's quite different. But the 10 centimeter per second is sort of a rough measure of the precision that you need in your radial velocity observations to capture these small accelerations using very precise spectrographs.
So what is the limit, minimum or maximum?
What is the, say that again, what is the?
Limit, it's any limit is maximum or minimum?
So, I mean, this is sort of what we need at the moment to measure, you know, these kind of changes that are, say, induced by dwarf galaxies. In principle, there could be even smaller changes that are induced by, let's say, primordial black holes, but we can't capture them at the moment. I mean, for example, another kind of thing that one could do in the future is look at the redshift drift, right? And that, I believe, could be done in sort of the next generation with the extremely large telescopes with very, very precise spectrographs. So there, the challenge there is having large enough collecting area, large enough buckets, photon buckets, so that you can make those kind of measurements. But at the moment, we're restricted to the galaxy, so we're focusing on sort of large-scale disequilibrium effects. As we increase the number of sources, that's another way of sort of mitigating the precision, which is sort of how I was responding to Tarun's question in terms of looking at dark matter subhalos.
Yeah, hello. So I have one doubt on that. Whatever you are measuring or comparing with observed P dot measurements, right?
Yes.
So how much precision you want for that?
So for the PB dot measurements, for the time rate of change of the binary period, you need, sort of roughly at the level of about 10 to the minus 13 second per second for the time rate of change of the binary period, roughly.
Okay. So one more doubt is, say, how are you making use of timing, pulsar timing in this measurement? So pulsar timing, actually, that sensitivity currently, what we have is around 1 microseconds to few hundreds nanoseconds level timing.
Right.
So you need to measure the P dot over the time to get that dynamic change, right?
Right.
So you need to do the timing again and again over the time. So so how are you measuring the change of P dot over time?
So you can express, effectively, you can express it either as a precision in your PB dot. By the way, we've mostly focused on PB dot. I'm not quite sure what you mean when you say P dot, right? So there are two types of derivatives that you can look at, right? You can either look at the time rate of change of the binary period, which we have mainly focused on, or you can look at the time rate of change of the spin period. But effectively, what determines all of these things is your frequency in the TOAs, which is effectively what leads to this timing precision on the PB dot, right? And so we require that the PB dot is different from 0 at the 2 sigma level. In order for binary pulsar to make it into our sample, PB dot has to be distinct from 0 at the 2 sigma level. It has to be measured at the 2 sigma level. We also need to have measurements of the parallax from pulsar timing. We also have to have measurements of proper motion from pulsar timing, not just PB dot measurements. But effectively, it does boil down to the precision on the TOAs.
Okay. Okay, thanks.
Thank you. Very nice talk. So, in near future, will it be possible to have map of dark matter density, as compared to currently you said that only single value maybe at I think disk. Close to disk.
Yeah. Absolutely. Yeah, that is very much what we're after. And so let me maybe that's a great question. Let me maybe emphasize that point a little bit more here. So this is. So this figure, maybe the best figure to show is this figure here. So what this is showing is, all our accelerometers across the galaxy, right? And the color bar is showing the contribution to the line of sight acceleration from dark matter versus the baryons, right? So the regions where you have the yellow, right, these are sort of caustics in the dark matter potential. And so this this particular case is shown here from a static galactic potential. But this is really what we aim to do with our direct acceleration measurements. We aim to produce these kind of maps of the dark matter from our direct acceleration measurements. We're not quite there. I mean, this is, you can see our maps are, so this is our observed acceleration map for the 26 binary pulsars, so it's still pretty sparse, right? But we're at the level where we can look at, we can clearly see the asymmetry below the disk and above the disk. But that's really where we're headed. We're aiming to make these detailed dark matter maps that currently are a little bit sparse, but we ought to be able to fill that in the very near future.
Thank you.
Thank you so much.